Hello and welcome to this video. We're going to be looking at the first example sheet of MATH2375, and in particular we're going to be looking at the problem B1. Okay, so let's get started. In problem B1 we give you two functions which are y1 equals 1 minus 4x and y2 which is 2x minus 1 squared. And what we ask you to do, first of all, is to calculate the Wronskian. So the Wronskian is nothing else but the determinant of the matrix comprised of the first function and the second function on the functions of one variable on the first row, and then their derivatives on the second row. Note that you can write down the transpose of that matrix, which means that you would have on the first column the functions and on the second column the derivatives. That wouldn't change the result because the determinant of the matrix is also the determinant of the transpose of that matrix. So let's just go on and write down what these functions are. So we have 1 minus 4x here. That derivative is minus 4. And then we have y2, which is 2x minus 1 squared. And that derivative is 2 times 2, that's 4. 2x minus 1. Okay? And to take the determinant, I'm just going to do the cross product in this direction. So I'm going to be doing 1 minus 4x times 4 2x minus 1 minus 4 times 2x minus 1 squared. And what I can notice here is the presence of 4 2x minus 1 on each side. So I'm going to factorize by this. I get 4 2x minus 1 in prefactor of, on the first term I had 1 minus 4x, and then the second term gives me, this is a plus here, this minus and minus sign give me a plus. So I just get a plus 2x minus 1. And ultimately then what I get is this comes down to minus 2x, so I get minus 8x, 2x minus 1. Okay, so that's the Wronskian. And there will be two special points that are going to be associated with these two functions, y1 and y2. These two special points are effectively when this matrix that I wrote down here is singular, in other words, when the Wronskian is equal to 0. So let's have a look at what these two special points are. So w of x equals 0. And what we get when w of x equals 0 is either x equals 0 or x equals 1/2. Okay, so this is just looking at what values of x cancel this polynomial here. Okay, so that's the first part of the question. Now, if we look at the second part of the question, so we ask you to use theorem 1 to show that y1, y2 cannot be solutions of a differential equation that is given to you here with continuous function p and q on the interval minus 1, 1. Let's have a look at this. So first of all, this theorem 1 is the existence and uniqueness theorem for second order differential equations. So theorem 1, that theorem says let px, p of x and q of x be continuous on an interval AB, and with that hypothesis, the theorem says that the equation y double prime plus p of x y prime plus q of x y equals 0 has a unique solution y on AB, so still our same interval, that satisfies a set of initial condition, which is y of x, x0, I'm going to call that x0 for my initial condition, equals alpha, and I want this alpha to be real. I'm also going to have y prime of x0 equals beta, which is real, and I want my initial condition, of course, to be within the same interval that I've specified, that I'm working on. Okay, so that's our theorem. So, well, first of all, we want to show that these functions are not solutions of the equation. So something has to be wrong with theorem 1. And the only glaring hypothesis that we've done here, which we can't check if we look at an equation of that form, is this hypothesis here, right? So let's have a look if we can plug in for these special points that we've identified. Let's have a look at whether what values the functions take, what are the initial conditions of these functions. So, first of all, we have a special point at x equals 0. So y1, let me remind you, y1 is 1 minus 4x. Its derivative is minus 4. And y2 was 2x minus 1 squared. And so the derivative of y2 is 4 2x minus 1. Let me just erase that here and put it there. So at x equals 0, y1 of x equals 0 is 1. Y prime 1 at x equals 0 is minus 4. And similarly for y2 at x equals 0, I get 1 as well. And y2 prime at x equals 0 is, if I plug x equals 0 in there, I get minus 4. Okay? So what we can notice here is that for x equals 0, our initial conditions for y1 and y2 are the same. But if we look back at the theorem, theorem 1 says, well, okay, so our hypothesis is p and q are continuous functions on AB, okay? So then the equation has a unique solution on that interval that satisfies the set of boundary condition. And you can see here that the set of boundary condition is shared between y1 and y2. Therefore, there isn't a unique solution to this equation that satisfies this. And as a consequence, what happens is that for these solutions, for these two functions to be solutions of that equation, p and q have to be discontinuous. Okay? So y1 and y2 share the same boundary condition. Sorry, initial conditions. This violates the uniqueness theorem. As a result, for both of these functions to be solutions of the equation, px and qx have to be discontinuous on the interval which was specified in the question, which is minus 1, 1. Okay? So that's the first part of the problem. The second part of the problem was looking at the second point, right? So we had another point, which is another special point, which is 1/2, right? So let's have a look at what these initial conditions would be at x equals 1/2. So y1 at x equals 1/2 is minus 1. y1 prime at x equals 1/2 is minus 4. y2 at x equals 1/2. So I'm looking again at the definitions of these functions. So y2 at x equals 1/2 is 0, and y2 prime at x equals 1/2 is, well, 0 as well. Okay? And here we have something quite funny that happens here, which is that disregarding y1, which looks legitimate, y2 should raise a red flag, a red warning in your head as a mathematician. You see a function that satisfies initial conditions that are 0 everywhere, and the equation that we're trying to work with is a linear equation that is homogeneous. That is to say, the right-hand side is 0. In other words, without specifying any boundary conditions or any initial conditions, this equation admits necessarily 0 as a trivial solution. And this solution, 0, has the same initial conditions as y2. So we can also find y3, which is identically 0 on the whole interval, minus 1, 1, which satisfies the same initial conditions as y2. Okay? And so these functions are not unique. Okay? So once again, this violates the uniqueness theorem, and we end up with the same conclusion as for x equals 0.